Welcome to The Explainer. Today, we're cracking open our planet's oldest secrets. We're going to look at how scientists can read the epic 4.5 billion-year-old story of the Earth using clues hidden deep inside solid rock.
I mean, think about it. It's the ultimate cold case. The crime scene is, well, the entire planet, and the events happened billions of years ago. So how in the world do we piece it all together? Well, we're going to go on a geochemical detective investigation, using clues at the atomic level to figure out the history of our planet's inner workings.
So here's our game plan. We'll start with the basics, Earth's chemical engine. Then we'll get into the high-tech tools these detectives use to actually read rocks. From there, we'll dive right into a huge scientific debate, follow the clues to the seafloor, and finally, see if we can get a verdict on what our planet's mantle really looks like.
Okay, let's get into it. To understand Earth's history, we've got to first understand how it organizes all its chemical ingredients. And geologists think about this in terms of these massive storage zones they call reservoirs.
You can almost picture the Earth as this giant, super slow-moving chemical factory. The main departments, if you will, are the mantle and the crust, and they are always trading materials. You've got magma rising up from the mantle to form new crust through volcanoes, and then you have old crust getting dragged back down into the mantle through subduction. This whole cycle has just been churning away for billions of years.
So, how do we track this ancient cycle? We need a special kind of tool, right? Something that can record time over billions of years? And this brings us to our main clue-finding technique, the incredibly powerful science of isotope analysis.
Isotopes are just different versions of the same element. They just have a few extra neutrons. Some of them, like carbon-12, are super stable and just stick around forever. But others are radioactive, which means they're unstable and they decay over time. And it's these radioactive isotopes that are the key to our whole investigation.
You see, this decay process, it works like a perfect, natural clock. When a rock first forms, it locks in a certain amount of a radioactive parent isotope. Then, over geologic time, that parent steadily decays and it transforms into a stable daughter isotope. The best part? The rate of this decay is absolutely constant and totally predictable.
And here's what makes this so incredibly powerful. The very moment that magma cools and crystallizes into rock, that whole system gets frozen solid. It's like a stopwatch starts ticking. So by measuring the ratio of parent-to-daughter isotopes in a rock sample today, scientists can calculate exactly how long ago that clock started. It gives us the precise age of the rock. It's amazing.
Okay, now that we have our clock, we can start solving some real mysteries. And this takes us to one of the biggest debates in all of geology. What is actually happening deep, deep inside the Earth's mantle?
This is the central question our isotopic clues are going to help us solve. For decades, you had two major theories competing with each other. Is the entire mantle, from top to bottom, just churning together in one giant convection cell? Or is it layered, with the upper and lower mantle barely mixing, kind of like oil and water?
So this gives us our two main suspects in this planetary investigation. The whole mantle theory says it's one huge blended reservoir. The layered mantle theory argues for at least two very distinct reservoirs that have evolved separately. The chemical clues hiding in the rocks, they should tell us which story is the right one. Now, to solve this mystery, scientists had to get their hands on samples from the mantle. But, we can't exactly drill down hundreds of miles, so they did the next best thing. They collected rocks that erupted from the mantle, right onto the seafloor. And when they did, they found two key types of basaltic rock. You can think of them as two key witnesses in our case. There are mid-ocean ridge basalts, or MORB for short, and ocean island basalts, or OIB. And at first, their stories seemed to completely contradict each other.
Yeah, the differences between them are pretty striking. MARB erupts all along this massive 40,000-mile-long mid-ocean ridge system, and its chemistry is surprisingly consistent, almost boringly so. OIB, on the other hand, erupts at these isolated hotspots like Hawaii, and its chemistry is all over the place, incredibly diverse.
Now, MORB's consistent chemistry tells a really clear story. Because it's sampling such a huge area, its uniformity is pretty conclusive evidence that the upper mantle is this vast, well-mixed reservoir. We also see that it's depleted, which just means that over billions of years, key elements were pulled out of it to form the continental crust.
So with this really powerful piece of evidence, we can start to build some real, quantitative models. We know the continents were basically extracted from the mantle, but when did this all happen? And how much of the mantle was actually involved?
By using that rubidium-strontium clock, but on a global scale,
geochemists were able to calculate a truly stunning number. They figured out that the mean age of all the continental crust on Earth is 2.1 billion years.
Now, let's be super clear here. This isn't the age of the oldest rock. It's the average age of all the stuff that makes up the continents. This one number gives us a critical timestamp for when that great chemical separation between the crust and the mantle really kicked into high gear.
And here is where the detective work gets really, really clever. Scientists did what's basically an accounting exercise, a mass balance calculation. They knew the chemical signature of the continents that were removed from the mantle. So that meant the remaining depleted mantle had to have a perfectly complementary signature. And their calculations showed the size of this depleted zone was bigger than just the upper mantle, but it was smaller than the whole mantle. This was a huge clue. It was pointing strongly toward a layered mantle. But there was still a problem. This didn't explain the wild chemistry of those ocean island basalts.
So how do we solve this final paradox? On the one hand, we've got MARB telling us the upper mantle is well mixed and uniform. But then we've got OIB, which come from these deep mantle plumes, telling us the mantle is also home to these pockets of ancient, really diverse chemistry. How could it be both at the same time?
Right. This apparent contradiction, that the mantle is somehow both boringly uniform and excitingly diverse, was a huge puzzle. It suggested that neither the simple whole mantle model nor the simple layered mantle model was the whole story. The truth had to be something a little more elegant. And then, in 1986, the answer arrived. And it came in the form of a brilliant, and let's be honest, a delicious-sounding metaphor, the marble cake mantle.
This model explains everything perfectly. See, when old oceanic crust subducts back into the mantle, it doesn't just dissolve like sugar in coffee. Nope. Instead, the powerful convection currents stretch it and fold it and swirl it into the surrounding mantle. This creates these ribbons of chemically distinct material, just like fudge swirled into vanilla ice cream. So MORB samples the well-mixed vanilla, giving us that uniform signature. But the deep OIB plumes can tap directly into one of those ancient enriched fudge swirls, which gives us their diverse and exotic chemistry. It all fits.
This elegant marble cake model just shows how these tiny atomic clues, locked away in volcanic rocks for billions of years, can reveal the grand, dynamic, and surprisingly beautiful story of our planet's inner workings. It reconciles all the evidence perfectly, and it leaves us with a final, pretty tantalizing question. If the Earth really is a marble cake, what other ancient chemical flavors are still swirled deep within the mantle, just waiting to be discovered?